Assalamualaikum, dear students. Today we are going to start new chapter, which is chapter number 10, and this chapter is about infinite sequences and series. So we are going to cover section number 1 of the chapter, which is about sequences. So in this section, we are going to define sequences, their convergence and divergence is discussed, and the limit of the sequences is also discussed. Then there are few theorems about the sequences and their limits and their convergence and divergence. So first of all, representing sequences. A sequence is a list of numbers a1, a2, a3, an in a given order. So there are 2 points to be noted. This is a list of numbers and in given order. So order matters in the list. Each of a1, a2, a3 is a1, a2, a3 and so on represents a number, and these numbers are called the terms of a sequence. For example, the sequence 2, 4 up till 2n has the first term 2, second term 4, third term 6 and so on, and nth term is 2n, right? So the integer n is called index of an. This integer n is called index of an and indicates where an occurs in the list. So this actually tells us the number of term in the list. Well, order is important, so to make sure that you don't forget, order is important. The sequence 2468 is not the same as 2648. In this case, A2 is 4, A3 is 6. But in this case, A2 is 6 and A3 is 4. So these two sequences are totally different sequences. We can think of sequence A1, A2, An as a function that sends 1 to A1, maps 2 to A2, 3 to A3, and in general n to An. So we can write the sequence or we can define the sequence that sequence is just a function from set of positive integers to the set of real numbers. Since we are discussing the real numbers right now, so the sequence is the function, or more precisely we can tell the infinite sequence. Infinite sequence, so there is the definition of infinite sequence. Infinite sequence of numbers is the function whose domain is the set of positive integers. That is the set of positive integers. So sequence can be described by writing rules that specify their terms like this. Nth term of the sequence is square root of an. We can write other terms using this formula. Similarly, this nth term for the sequence is given by this formula. So we can find the other terms. So there is a representation of the sequence by listing the terms. Like this sequence can be terms of this sequence can be listed this way, and the terms of this sequence can be listed in this way. And sometimes we write the sequence in this notation. So these are few notations to represent the sequences. Well, convergence and divergence of sequence. So sometimes the number in a sequence approach a single value as the index n increases. This happens in this sequence. For example, this is the sequence 1, 1 over 2, 1 over 3, and its nth term is 1 over n. And as n increases, this nth term decreases and it approaches towards 0. So this leads us to define the convergence and divergence of the sequence. A sequence an converges to the limit L if for every positive number epsilon their corresponding integer n such that an minus L mod is less than epsilon whenever n is greater than n. So we can have a look at this in using this picture. Here you can have a number n, and after this n, we can see the n terms. So now this axis represents n, and this axis represents an. All right. So this is the graph of the sequence, and after this number, the value of an lies in this rectangle, and this rectangle represents r minus the lower bound of this rectangle is r minus epsilon, l minus epsilon, and upper bound is l plus epsilon. So l lies in the center, so an is equal to l, and here an is l plus epsilon, a n minus. So every term after this number lies within the rectangle. So then we can say that this sequence approaches to L, and this sequence is convergent sequence. And if we cannot find any number n such that this relation holds, or this condition holds, then the sequence is called divergent sequence, or we say that the sequence diverges. And if the sequence converges, then we write limit of an as n approaches to infinity is L, or we simply say that an approaches to L and call L the limit of the sequence. So you are already familiar with the functions and their limits, so this is not a new concept for you. Now example, show that the limit of 1 over n approaches to infinity is 0. So using the definition of the limit, we just have to find the value of n for which 1 minus 0 is less than epsilon. So this is L in our case, L. So consider this inequality. 1 minus n minus 0 is less than epsilon. This gives us the relation 1 over n is less than epsilon, and this implies n is greater than 1 over epsilon. We just reciprocate it and have this relation. So this actually leads us to the conclusion that if n is any integer greater than 1 over epsilon, the inequality will hold for all n greater or equal to n. And this means limit of 1 over n as n approaches to infinity is 0. Next, show that the sequence 1 minus 1, 1 minus 1, and so on diverges. So this is a sequence with oscillating terms 1 and minus 1. So it oscillates between two values, right? So suppose that the sequence converges. So initially we suppose otherwise. We have to prove that this is divergent, and we suppose otherwise that it's converges to n. Then by the definition, the numbers in the sequence eventually get arbitrarily close to limit L. So this cannot happen if they keep oscillating between 1 and minus 1, right? So we can see by choosing epsilon is equal to 1 by 2, or any epsilon which is less than 1 in the definition of the limit. Then all the terms of the sequence with index n larger than some n must lie within epsilon 1 is equal to 1 over 2 of n. Since the number 1 appears repeatedly as every other term of a sequence, so we must have that the number 1 lies within the distance epsilon is equal to 1 over 2 of n. So it follows L minus 1 is less than 1 over 2, or equivalently L lies between 1 over 2 and 3 by 2, right? So by expanding this absolute value inequality. Likewise, the number minus 1 appears repeatedly in the sequence with arbitrarily high index. So we must also think of that this is the limit. In this case, L minus negative 1 absolute value should be less than 1 over 2, or equivalently we have this result that is the solution of this inequality. But the number L cannot lie in both of the intervals 1 over 2, 3 by 2 and minus 3 by 1 minus 1 by 2, because they have no overlap. Therefore, no such limit L exists, and so the sequence is divergent sequence. And as I told you in the middle of the solution, that the same argument works for any positive integer epsilon, positive number epsilon, not an integer, positive number epsilon which is less than 1. So this is not just the case for epsilon is equal to 1 over 2. You can try it for any epsilon which is less than 1. and positive value of that set. So there is another concept of divergence. The sequence an diverges to infinity if for every number m there is an integer n such that for all n greater or equal to n, an is greater than n. If this condition holds, we write that limit of an as n approaches to infinity is infinite, or an approaches to infinity. So that is if the term value of the term increases indefinitely as n increases, then the limiting value of the ns term is infinite as n approaches to infinite. So this such sequence is called the sequence diverges to infinity. Similarly, sequence diverges to negative infinity. So for this, if for every number m there is an integer n such that for all n greater or equal to n, an is less than n. We are thinking of a very small number, an is even smaller than that. Then we say that the sequence diverges to negative infinity, and we write it as limit of an as n approaches to infinity is equal to negative infinity, or we can say that an approaches to minus infinity. Well, a sequence may diverge without diverging to infinity or negative infinity, as we see in previous example. Now there is a theorem about the relation between two sequences. Let a and bn be the sequence of real numbers. That is, these are the functions from n to r. So n maps to an, which is a real number. And let a and b be the real numbers. The following rules hold if limit of an as n approaches to infinity is equal to a, that is limit of an is a, and bn approaches to b. So first rule is called sum rule. This is the limit of sums is equal to sum of limits. Similarly, difference rule, limit of differences is equal to difference of limits. Constant multiple rule, and these rules are quite same as you have already learned in the section of functions in calculus 1. Similarly, we have product rule of limits, quotient rule of limits. So there is the application of this theorem. Limit of minus 1 over n, it can be written as minus 1 limit of 1 over n, and we know that limit of 1 over n is 0. So using the constant multiple rule, we can say that limit of minus 1 over n as approaches to infinity is also 0. Similarly, limit of 5 over n square as n approaches to infinity can be written as 5 times limit of 1 over n as n approaches to infinity times limit of 1 over n and approaches to infinity. And now we know that this is 0, this is 0, so product rule tells us limit of this function is also 0. This sequence is also 0. Now there is a warning. While applying theorem 1, it does not say, for example, that each of the sequence S and Bn have limits if their sum has the limit, okay? It does not mean that if an and bn both have limits, their sum will also have a limit. For instance, we have a sequence an, 1, 2, 3 and so on. Bn is also a sequence with minus 1, minus 2, minus 3. Both diverges. Both of the sequences are divergent, but their sum is convergent. Because, of course, this is clearly convergent to 0. Every term of this sequence is 0. Well, the sandwich theorem for the sequence, and again you are familiar with the name, the sandwich theorem for the limits in calculus 1. So let a and b and cn be the sequences of real numbers. If bn lies between an and cn, that is nth term of Bn lies between nth term of An and nth term of Cn for all n beyond some index n, that is n greater than n. And if limit of An as n approaches to infinity, that is the limit of left sequence and limit of right sequence both are equal, then we conclude that limit of the central sequence Bn is also equal to n. So the immediate consequence of this theorem, if absolute value of Bn is less than n, less than Cn, and Cn approaches to 0, then Bn approaches to 0, because Bn lies between, using this inequality, we can write Bn lies between Cn and minus Cn. So we know that 1 over n sequence approaches to 0. So this yields the result that cos n over n approaches to 0, because cos n over n can be written as, now cos n, in fact let me explain this. Cos n lies between 1 and minus 1, you know it very well, right? Now dividing the inequality by n, because n is a positive number, so my inequality will remain same. Minus 1 over n is less or equal to cos n over n less or equal to 1 over n. And minus 1 over n and 1 over n both are approaching towards 0. So the bi-sandwich theorem, or limit of cos n over n is also 0. Now 1 over 2n, 1 over 2 to the power n is greater or equal to 0 but less or equal to 1 over n. And 1 over n approaches to 0, and 0 of course is convergent with the limit 0. So the limit of 1 over 2n is also 0. Now the continuous function theorem for sequence. Let an be a sequence of real numbers if an approaches to L and if f is a function. An approaches to L, that is, this sequence is a convergent sequence and its limit is L. And if f is a function, f is some other function, f is a function that is continuous at n, that is the limiting value n, and defined at all an, then f of an approaches to f of n, right? F of an approaches to f of n. So there is an example. Show that square root of n plus 1 over n approaches to 1. So we know that square root of n plus 1 over n approaches to 1. And how can we be so sure that this approaches to 1? Because n plus 1 can be written as 1 plus 1 over n, and limit of this as n approaches to infinity is equal to 1. So this sequence approaches to 1. Now taking fx is equal to square root of x. Now taking fx is equal to square root of x and L is equal to 1. So previous theorem actually tells us f of an approaches to f of n. So what is f of an? An is going to be this, n plus 1 over n, and f of an is square root of n plus 1 according to this definition of fx. So f of an approaches to f of L, right? So this means, now since an is equal to this, so f of an, this is f of an, and this is f of n, right? So this implies limit of this sequence is 1. Next theorem, suppose that fx is a function defined for all x greater or equal to n naught. Fx is a function. Now we are talking about a function x greater or equal to n naught, and that an is a sequence of real numbers such that an is equal to f of n for n greater or equal to n naught. Then limit of an as n approaches to infinity is equal to n whenever limit of fx as x approaches to infinity is L, right? So we are going to relate the concept of limit and sequence to the concept of limit and functions. So again, let's read the statement. So we have a function defined for all x greater or equal to n naught, and an is a sequence. We have a sequence of real numbers such that what is the relation between a and f? An and f, that an is equal to f of n for n greater or equal to n naught. Then limit of an as n approaches to infinity is l whenever if fx has a limit as x approaches to infinity, then the sequence an has also a limit as n approaches to infinity. And you can prove it yourself. All the proof is given here, and this is a straightforward implementation of the definition of limit. Okay, next, show that limit of natural log of n divided by n is 0 as n approaches to infinity. So the function ln x over x is defined for all x greater or equal to n and agrees with the given sequence positive integer. So therefore, the theorem for state according to theorem 4, limit of log n as n approaches to infinity must be equal to limit of log x as x approaches to infinity if this exists. Okay, so a single application of L'Hopital rule, we can prove this limit exists and the limit of this function is equal to 0. So this shows that the limit of natural log of n over n as n approaches to infinity is 0. Okay, next example. Does the sequence whose nth term is a n is equal to n plus 1 over n minus 1 raised to the power n converge? If so, find the limit. So the limit leads to the intermediate form, okay, when we plug in n approaches to infinity. So we are having 1 to the power. The direct plugin actually shows 1 to the power infinity. So this is the indeterminate form, and by using L'Hopital rule, we can find the limit if it does exist. So by taking natural logarithm, so that we can apply the L'Hopital rule, like natural logarithm on both the sides, log of an is equal to n log of n plus 1 over n minus 1. So limit of n approaches to infinity, natural log of n is equal to limit of n multiplied by limit of natural log of n, or we can write it as natural log of n plus 1 over n minus 1 divided by 1 over n. And this manipulation is done to convert this infinity multiplied by 0 form to 0 by 0 form. So now this is in 0 by 0 form. We can use L'Hopital rule to find the limit of this function, and by using L'Hopital rule we have the limiting value of this sequence is equal to 2. Now since log of an approaches to 2 and fx is equal to ex is continuous, so an is equal to e to the power log of an, which is equal to e square, and this implies an approaches to e square. Thus this sequence converges because this function fx converges. Next here, the following 6 sequences converge to the limits listed below. So here we go. This is the first we have already proved. This is the second result. That is, if we have the square root nth square root of n, then this converges to 1. X nth square root nth root of x is also 1 as x greater than 0. Similarly, limit of x to the power n is equal to 0. Limit of 1 plus x to the x over n to the power n is e to the power x, and limit of x n over n factorial is 0 for any x. And these formula containing x 3 to 6 all contains x in the definition. So x remains fixed as n approaches to infinity. So once x is chosen, then x remains fixed. and try to prove all these results yourself. So my favorite thing to write, do it yourself. Alright, so there are examples of limit. The limit of natural log of n square over n. We can write it as 2 times natural log of n over n, and we know that this sequence converges to 0. So by using the constant multiple rule, we have 2 times 0 and this is equal to 0. So this sequence converges to 0. Next, n minus 2 over n to the power n can be written in the form 1 plus minus 2 over n to the power n, and this approaches to e to the power minus 2 with the help of formula 5 in the previous example, list of formulas. So similarly, we can have minus 1 over 2 to the power n approaches to 0, and formula 4 actually gives us this result. Next, recursive definitions. So far we have calculated each an directly from the value of n, but sequences are often defined recursively by giving the values of the initial term or the terms and a rule called a recursion formula for calculating any later term from the terms that precede it. For example, the statements a1 is equal to 1 and an is equal to n times an minus 1 for n greater than 1 defines the sequence 1, 2, so on of the factorials. With a1 equal to 1, we have a2 equal to 2, a1 equal to 2, a3 equal to 3, and so on, a2 is 6, and so on. So there is another example. The statement a1 is equal to 1, a2 is equal to 1, and an plus 1 is given by this recursion formula. An plus 1 is equal to an plus an minus 2 for n greater than 2, rather greater or equal to 2, because when n is equal to 2 we will have a3, so greater or equal to 2. Defines the sequence 1, 1, 2, 3, and this is called the Fibonacci number sequence. With a1 is 1, a2 is 1, so we have a3 is 1 plus 1, which is equal to 2, a4 is 3, and so on. So this is the Fibonacci, very well known Fibonacci number sequence. Now, two concepts that play a key role in determining the convergence of a sequence are those of the bounded sequence and monotonic sequence. Now, we are going to define bounded and monotonic sequences. So, a sequence an is bounded from above if there exists a number m such that that every term of the sequence less or equal to this number m for all n. The number m is called the upper bound for an. If m is an upper bound for an, but no number less than m is an upper bound for an, then m is the least upper bound for an. For example, if we have the sequence 1 over n, if we list the terms of the sequence, we have 1, 1 over 2, 1 over 3, and so on. So, every term of the sequence is less or equal to 1, right? So, in this case, we have m, and m is equal to 1, and an is less or equal to n. So, we have m. So, we have upper bound for this sequence, which is 1. But 2 is also upper bound of the sequence because every term is less than 2 as well. 3 is also upper bound, but we cannot find a number which is less than n and which satisfies this property. So, this 1 is called the least upper bound for this sequence an. Now, a sequence an is bounded from below if there exists a number m such that an is greater or equal to n. So, the opposite concept, bounded from above and bounded from below for all n. The number m is the lower bound for an. If m is the lower bound for an, but no number greater than m is the lower bound for an, then m is the greatest lower bound for an. Right? So, the greatest lower bound, the least upper bound. So, this is the concept of boundedness. If an is bounded from above and below, then an is bounded. So if an is bounded from above and below both, that is an is bounded below as well, bounded above as well, then this is called bounded sequence. So if is not bounded, then we say that an is unbounded sequence. So for a sequence to be bounded, this is important, this is bounded above and bounded below. The sequences 1, 2, 3 to has no upper bound because it eventually surpasses every number m. However, it is bounded below by every real number less than or equal to 1. The number m is equal to 1 is the greatest lower bound. Okay, so this is the greatest lower bound of the sequence. Because this is bounded below by 0 as well, this is bounded below by -1 as well, bounded below by -2 as well, but this is the greatest one for which this condition holds, that is an is greater or equal to, right? So m here is 1, the largest value of m here is 1. So an is greater or equal to 1. So this is the greatest lower bound. So this is greatest among the list of lower bounds, right? You can make it understand as well. You can have the idea by thinking of the greatest among the lower bounds. So this is called the greatest lower bound. And similarly, smallest among the upper bounds is called the smallest upper bound. So the sequence 1 over 2, 2 over 3, 3 over 4, where is n over n plus 1 is bounded above by every real number greater than 1 or equal to 1. The upper bound m is equal to 1 is the least upper bound, right? This is bounded above by 2, bounded above by 3, bounded above by 4, and so on. But this is the least among the upper bounds. So this is called the least upper bound. The sequence is also bounded below by every number less than or equal to 1 over 2. So it has a lower bound, it has an upper bound, and this 1 over 2 is the greatest lower bound. So this means this is the bounded sequence. So a sequence is non-decreasing. Another definition, non-decreasing, if an is less or equal to an plus 1. That is, next term is either greater than the previous term or equal to the previous term for all n. So this type of sequence would it be? So the sequence is non-increasing if an is greater or equal to n plus 1. That is, if every next term is less or equal to the preceding term. So the sequence an is monotonic if it is either non-decreasing or non-increasing. So this is another definition, monotonic sequence. So sequence 1, 2, 3 up till n is non-decreasing, and this sequence is again non-decreasing. This sequence is non-increasing because every term is less, the next term is less than the previous term. The constant sequence is both non-decreasing and non-increasing. This sequence is not monotonic because we cannot find the relation between the terms for all n. Okay, next theorem, the monotonic sequence theorem. So this theorem states that if a sequence an is both bounded and monotonic, then the sequence converges. Okay, if the sequence is bounded and monotonic, then the sequence converges. So here is the proof. If we have a sequence an which is non-decreasing, L is its upper bound, and we plot the points 1, 2, 1a1, 2a2 in the xy plane. If M is an upper bound of the sequence, all these points will lie on or below the line y is equal to n, right? So we can have figure as well. Here is the figure. So this is the line y is equal to m. So all the points lie below this line because m is the upper bound, right? The line y is equal to L is the lowest such line. None of the points n, a, n lies above y is equal to L, but some do lie above any other lower line. Y is equal to L minus epsilon if epsilon is a positive number, is not an upper bound. So the sequence converges to L because an is less or equal to L for all values of n, and given any epsilon greater than 0, there exists at least one integer n for which an is greater than L minus epsilon. The fact that an is non-decreasing tells us further that an is greater than L minus epsilon. So thus all the numbers an beyond the nth number lie within epsilon rectangle of L. This is precisely the condition for L to be the limit of the sequence n. So thus the sequence converges. So initially we assume that the sequence is non-decreasing and it has a least upper bound. Okay, and we proved that the sequence converges. Similarly, we can prove this result for non-increasing functions as well, and this is an exercise for you. So that's all for today.